Welcome, everyone, to another deep dive. We always love hearing from y'all, and we've gotten some really fascinating stuff lately, all about multiplication and division.
Yeah, it's great.
And, on the circuit, these seem like, some of the most basic math tools we learn, right? Like the things you learn right when you start out with math.
Absolutely.
But what we want to do today is really dive deep into these operations and see what's going on beneath the surface. We want to understand not just how they work, but also why they're so useful.
Yeah, and how they connect to so many other things. It's easy you take them for granted, but when you start looking deeper, there's a lot more to them than meets the eye.
And luckily, we have this awesome guide here that really breaks it all down.
Yeah, this is a really comprehensive guide. It starts with those foundational concepts and then takes us all the way to some more advanced applications and interesting connections.
I think you're going to be surprised by some of the things we discover. I know I was when I was reading through this.
Yeah, even for something as familiar as multiplication and division, there are always new insights to uncover.
Okay, so let's start with multiplication. What's the fundamental idea here? The guide kicks things off with a classic example, cookies.
Yeah, who doesn't love a good cookie analogy?
Okay, so imagine you've got 3 friends coming over, and you want to give each of them 4 cookies. How do you quickly figure out how many cookies you'll leave in total?
Right.
Well, you could add 4 plus 4 plus 4, but that's kind of a long way to go, especially if you have more friends.
Yeah, and that's where multiplication comes in.
Exactly. Multiplication gives us this awesome shortcut
Mm-hmm.
that lets us quickly calculate the total when we're adding the same number multiple times. So in this case, 3 friends times 4 cookies each equals 12 cookies total.
Exactly. It's all about efficiency and making those calculations much faster.
And there are some key terms we need to know here. The numbers we're multiplying, the 3 and the 4, are called factors.
Right.
And the result, the 12, in our example, is called the product.
Makes sense.
Now, the guide goes on to show us that there's more than one way to think about and visualize multiplication.
And that's really helpful because sometimes one way of looking at it just clicks better than another.
Right. One way is to think about groups of things.
It's like our cookies example.
Exactly. So instead of 3 friends, let's say you have 2 bags of candy, and each bag has 5 candies in it. You have 2 groups, each with 5 candies.
And you can see that as 5 plus 5, which equals 10.
Or you can use multiplication and simply do 2 bags times 5 candies per bag and get 10.
Much quicker.
But there's a super important point here that the guide emphasizes. Those groups have to be equal in size. If one bag had 5 candies and the other had 7, then we couldn't just multiply to get the total.
Right. Multiplication works when we're dealing with the same quantity repeated multiple times. That's the key idea.
So those equal groups are essential.
Absolutely.
Now, another way to visualize multiplication is through something called arrays. Have you ever seen an array?
Oh, yeah. Arrays are very visual, which can be really helpful. They're just arrangements of objects in equal rows and equal columns.
I love that example they use in the guide. An egg carton.
Perfect example.
So if you have an egg carton with, let's say, 2 rows, and each row has 6 eggs.
You can multiply 2 rows by 6 eggs per row to find the total number of eggs.
Exactly, and that gives you 12. And the cool thing is, arrays are everywhere.
Oh, yeah.
Think about a muffin tin, or the seats in a movie theater, or even just the tiles on your floor. Those are all arrays.
They really are. It's a pattern we see all around us.
And here's something that I thought was so neat. The guide points out that if you flip that egg carton sideways, so now you have 6 rows with 2 eggs in each row.
You still have 12
You
eggs.
still get 12. It's 6 rows times 2 eggs per row, which still equals 12. And this actually leads to one of those cool rules we're going to talk about in just a minute.
Right. It hints at the idea that the order in which you multiply doesn't actually change the result.
Exactly. Before we get to those rules, the guide does a great job of showing us all the real-world places where we use multiplication.
And honestly, it's more common than we might realize at first.
It really, so like if you buy 4 packs of trading cards and each pack has 8 cards in it, you'd use multiplication to find the total number of cards you have, right?
4 packs times 8 cards per pack.
Yeah. Or if a movie ticket costs $9 and you're buying tickets for 5 people, you use multiplication to find the total cost.
$9 per ticket times 5 tickets.
Even figure out how many days are in 3 weeks, that's multiplication.
7 days per week times 3 weeks.
And if you're setting up chairs for an event and need 6 rows of chairs with 5 chairs in each row, multiplication helps you figure out how many chairs you need in total.
6 rows times 5 chairs per row. It's everywhere.
We're multiplying all the time while we're not even thinking about it.
It's such an ingrained part of how we think about quantities and groups.
Okay, so now let's get to those cool rules the guide talks about, the ones that make multiplication even easier.
Okay, yeah, these are like little shortcuts that can really simplify things.
The first one is called the commutative property.
Big word.
Big word, but it's actually a pretty simple idea. It basically says that the order in which you multiply the numbers doesn't affect the answer. So A times B will always give you the same result as B times A.
Right, like with our egg carton, 2 rows times 6 eggs per row is the same as 6 rows times 2 eggs per row. It's still 12 eggs either way.
Exactly. And the guide gives us another example. 3 times 4 equals 12, and 4 times 3 also equals 12.
And if you think about it visually with those arrays, a 3 by 4 array has the same number of objects as a 4 by 3 array.
And this isn't just some abstract math rule. It can really help us make calculations easier.
Oh, absolutely. Like if you had to multiply something like 4 times 5 times 4, it's much easier to start by doing 4 times 5, which is 20, and then multiply that by 4 to get 80.
Yeah, instead of trying to do 4 times 4 first and then multiplying by 5.
Much smoother that way.
So the commutative property can really help us streamline our calculations.
Mm-hmm.
Now, the next rule is called the associative property.
Another one of those big words.
This one comes into play when we're multiplying 3 or more numbers. It says it doesn't matter how we group those numbers, the product will be the same. So A times B times C is equal to A times B times C. The guide gives the example of 2 times 3 times 4. You could first multiply 2 times 3 to get 6, and then multiply 6 by 4 to get 24.
Or you could group the 3 and 4 first.
You got it. So 3 times 4 is 12, and then 2 times 12 is also 24. The parentheses just tell us which multiplication to do first.
But no matter which way you group them, you end up with the same product.
And just like the commutative property, this could be super helpful.
Especially when you're working with multiples of 10.
Oh, absolutely. Like the guide's example, if you're multiplying 2 times 5 times 7, it's easiest to start by multiplying the 2 and the 5, which gives you 10, and then just do 10 times 7, which is 70.
Yeah, much easier than doing 5 times 7 first and then multiplying by 2. It's all about using those properties to make the calculations as simple as possible.
Exactly. So we've got the basic idea of multiplication, and we've got some cool rules to help us. But what happens when we have to multiply bigger numbers, numbers with more than one digit? That can seem a little intimidating.
Yeah, it can get a little more complex, but there's a systematic way to do it.
The guide walks us through what's called the standard algorithm,
It's the method most of us learned in school.
and it really breaks it down into manageable steps. Let's try it out with their example, 23 times 19.
Okay.
First, we write the numbers vertically, making sure the ones place is lined up with the ones place, the tens place with the tens place, and so on.
Right, so they're stacked neatly on top of each other.
Then we take the ones digit of the bottom number, which is 9, and we multiply it by each digit of the top number, starting from the right.
Okay, so 9 times 3 first.
Right, which is 27. We write down the 7 and carry over the 2.
That little 2 above the tens place.
Then we do 9 times 2, which is 18, and we add that carried over 2 to get 20.
So now we have 207.
Yep, and this is where place value is super important, like you were saying earlier. That carried over 2 represents 2 tens, and we're essentially adding it to the result of 9 times 2, which is also in the tens place.
It all has to line up.
Exactly. Okay, so now we move to the tens digit of the bottom number, which is 1. But remember, it's actually in the tens place, so it really represents 10.
So we need a placeholder.
We do. We put a 0 in the ones place of our next line to show we're working with tens now. Then we multiply that 1 by each digit of the top number, just like before.
Okay, so 1 times 3 is 3, and 1 times 2 is 2.
So we have 230, and finally we add those two results together, 207 plus 230, we get our final answer, 437. So 23 times 19 equals 437.
Nice. And notice how that 0 placeholder is so crucial. It makes sure we're adding up numbers in the right place values.
Absolutely. It keeps everything organized and prevents us from making mistakes.
It's like a little reminder that we're working with tens now.
So what about multiplying even larger numbers, like 452 times 67? The guide tells us that we can use the same standard algorithm.
Same process, just a few more steps.
So first we multiply 452 by the ones digit of 67, which is 7. Let's see, 7 times 2 is 14. Write down 4, carry over the 1. 7 times 5 is 35, plus the carried over 1 is 36, so write down 6 and carry over the 3. And finally, 7 times 4 is 28, plus the 3 is 31. So our first partial product is 3164.
Partial product, right?
Yeah, because it's just part of the final product. Now we do 452 times the tens digit of 67, which is 6.
And remember, that 6 really represents 60.
So we start by putting a 0 in the ones place as our placeholder. Then 6 times 2 is 12, carry over the 1. 6 times 5 is 30, plus 1 is 31, carry over the 3. And 6 times 4 is 24, plus 3 is 27. That gives us 207120.
And then we add those two partial products together.
Right, 3164 plus 27120, which equals 30284.
So 452 times 67 equals 30284. It might seem like a lot of steps, but it's really just breaking it down into smaller, simpler multiplications.
And then adding those results together.
And that's the key. It makes those bigger problems much less intimidating.
So that's multiplication in a nutshell, making numbers bigger through repeated addition and with some helpful rules and a systematic approach.
Now let's flip things around and talk about division.
Right, the guy explains that division is essentially the opposite of multiplication.
Exactly. It's the inverse operation. While multiplication combines equal groups, division takes a total and splits it up into equal parts or group.
And like they say in the guide, think about sharing a pizza.
Gotta be fair.
You want to make sure everyone gets an equal slice.
Equal distribution, that's a key idea with division.
Now, we can write division in a few different ways.
It can get a little confusing, but it's good to know them all.
There's the division symbol, the obelisk, like 12/4 equals 3.
The one that looks like a plus sign with dots above and below it.
Then there's the fraction with a slash, like 12/4 equals 3.
Or we can write it with a horizontal line with the dividend, the number being divided on top, and the divisor, the number we're dividing by, on the bottom.
And then there's that long division symbol, or the division bar, like 412, which also means 12 divided by 4. They all represent the same operation.
Just different ways of writing it.
And just like with multiplication, we have some terms that help us talk about division. The number being divided is the dividend, the number we're dividing by is the divisor, and the result of the division is the quotient.
Got it.
And sometimes when we divide, things don't divide perfectly evenly, and we have some left over.
That's the remainder.
The guide uses this example. If you have 13 cookies and you want to share them equally amongst 4 friends, each friend gets 3 cookies and there's 1 cookie left over.
Aw, poor leftover cookie.
So 13 divided by 4 equals 3 with a remainder of 1.
Makes sense.
Now, the guide goes back to those ideas of equal grouping and equal sharing, but this time through the lens of division.
So like the opposite of what we were doing with multiplication.
Exactly. For equal grouping, they use the example of having 15 balloons and wanting to give 3 balloons to each friend.
So you're figuring out how many friends you can give balloons to.
Right. So we divide 15 balloons by 3 balloons per friend, and that tells us we can give balloons to 5 friends. For equal sharing, they use the same 15 balloons, but this time we want to share them equally among 5 friends. So we divide 15 balloons by 5 friends, and we find that each friend gets 3 balloons.
So with equal grouping, you're figuring out the number of groups.
And with equal sharing, you're figuring out the size of each group.
But they both use division to get the answer.
Okay, so just like with multiplication, we often need to divide larger numbers, numbers that are too big to easily do in our heads.
And that's where long division comes in handy.
The guide shows us how to do long division with the example 84 divided by 6.
Okay, let's walk through it.
We set up the problem with the long division symbol. We look at the first digit of the dividend, which is 8, and see how many times the divisor, 6, goes into it. It goes in once, so we write a 1 above the 8. Then we multiply that 1 by 6 to get 6, and write the 6 below the 8.
And then we subtract.
We subtract 8 minus 6, which gives us 2. Then we bring down the next digit of the dividend, the 4, and put it next to the 2, making it 24. Now we see how many times 6 goes into 24.
It goes in exactly 4 times.
We write that 4 next to the 1 in the quotient. Then we multiply 4 by 6 to get 24, and we subtract 24 minus 24.
Which leaves us with 0.
So our remainder is 0, and we're done. 84 divided by 6 equals 14.
And notice how we use multiplication along the way, like 1 times 6 and 4 times 6.
That really shows the close connection between multiplication and division.
They're inverse operations, so they work together.
Speaking of which, the guide has a section called Multiplication and Division, Best Friends.
I love that.
It explains that these two operations are inverses of each other, which means one undoes the other.
Like opposite actions.
Exactly. They give us this great example of a fact family. If we know that 3 times 5 equals 15,
then we automatically know that 15 divided by 5 equals 3, and 15 divided by 3 equals 5.
it's like they're all part of the same family.
And knowing this relationship can make things so much easier.
It can. Knowing your multiplication facts can help you with division and vice versa.
And it's also great for checking your work.
You got it. If you've done a division problem, you can multiply your answer, the quotient, by the divisor to see if you get back the original dividend. So if you calculated that 84 divided by 6 is 14, you can multiply 14 by 6, and if you get 84, you know you did it right.
It's a quick and easy way to make sure you're on the right track.
And this whole inverse relationship isn't just for checking work, though. It can also help us solve those problems where there's a missing number.
Oh yeah, like those fill-in-the-blank problems.
Exactly. So if we see an equation like what times 5 equals 30, we can use the inverse operation division to figure it out. We can ask ourselves, what's 30 divided by 5? And the answer is 6, which is also the missing number in our original multiplication problem.
Like a little puzzle you can solve by using the opposite operations.
Super useful. Now, the guide finishes up by answering some frequently asked questions about multiplication and division.
I always love those FAQ sections.
Me too. They clear up a lot of confusion. So one question is, what happens when you multiply any number by 0?
And the answer is,
Always 0.
it's like having 0 groups of something.
Like if you have 5 groups of 0 cookies, you still have 0 cookies. Another question, what happens when you multiply a number by 1?
In that case, the number stays the same.
Right. Like one group of 7 apples is still just 7 apples.
It's like the number's identity doesn't change.
Okay, here's a tricky one. Does order matter in division?
That's a good question.
And the answer is big yes. Like 10 divided by 2 is 5, but 2 divided by 10 is 0.2. So order definitely matters.
Totally different answer.
Then the guide asks, can you divide by 0?
Ooh, a classic.
And the answer is no. It's not possible to divide by 0. It just doesn't work mathematically. Then they explain again what a remainder is, the amount left over after we've divided into equal whole groups.
So it's like the extra bit that can't be evenly split.
They also sum up the relationship between multiplication and division. Multiplication combines equal groups, while division splits a total into equal groups. And they even give us some tips for learning multiplication tables.
Oh yeah, like skip counting and looking for patterns.
And finally, they talk about when we use each operation in real life.
Right, like when to multiply and when to divide.
Multiplications for when we need to find the total of several equal groups, and divisions for when we want to split a total into equal groups or figure out how many groups of a certain size we can make.
It's all about applying what we know to real-world situations.
So as we wrap up this deep dive, it's clear that multiplication and division aren't just basic math facts. They're incredibly important tools we use all the time, whether we realize it or not.
They really are fundamental to how we understand and interact with the world around us.
And that guide you shared, it really highlights how far-reaching these operations are, and it encourages us to keep exploring the world of numbers.
Absolutely. There's always more to learn and discover.
And here's a final thought for you all to ponder. We've been talking about multiplication and division in the context of numbers, but maybe they have parallels in other parts of life, too.
Oh, I like that.
Like, could multiplication be seen in the way that combined efforts or resources can lead to bigger, more impactful results? And could division be reflected in how we share responsibilities or distribute resources fairly?
That's a really interesting way to think about it.
It's fascinating to consider how these mathematical concepts might show up in unexpected places, shaping our world in ways we might not even notice.
Makes you think, for sure.
Thanks for joining us on this deep dive.
Always a pleasure.
We'll see you all next time.
Bye, everyone.